Hello friends, welcome to lecture series on matrix analysis with applications. So in the last few lectures we have seen that what vector spaces, subspaces are and what are their basic properties. We have also studied basis and dimension of vector spaces and subspaces. Now this lecture basically deals with linear transformation, what linear transformation is and how we can find out a linear transformation from V to W. So let us see now what linear transformation is. You see, let V and W be two vector spaces over the field F. A linear transformation, which is also say LT, from V into W is a function from V into W such that T of alpha u plus V is equal to alpha T u plus T V for every u v in V and for all scalars alpha in field. So basically what linear transformation is, basically you see that T is a linear transformation from a vector space V to vector space W over the field F if for every V1 V2 in V and for every alpha in field T of alpha V1 plus V2 is equals to alpha times T of V1 plus V2. Now this alpha V1 is nothing but scalar multiplication of alpha with a element of a vector space. So I am not putting dot here, it is understood that it is alpha dot V1. Okay. Similarly, this T V1 is an element of W. You see, we have vector space V, we have vector space W, and we define a linear transformation T from V to W. If we have any element say V here, the image of this element in W is simply TV. Okay. So this TV is nothing but an element of a vector space W, this vector space W, and this T V2 is also element of vector space W. So this alpha into T of V1 means scalar multiplication of alpha with element of W. Okay. So I am not putting dot here, it is understood that this is nothing but alpha dot T of V1. So basically if this property hold for every V1 V2 in V and for every scalar alpha in field, then we say that T is a linear transformation. Now this property can also be stated as, we can also say that T of V1 plus V2 is equals to T of V1 plus T of V2, first property, and second property is T of alpha V1 is equals to alpha of T of V1 for all V1 V2 in V and alpha belongs to field. Okay. So we club these two property here in the in this step. Okay. So we can also state this single property as these two properties. So if a function T from V to W satisfy these two property, then we say that T is a linear map or a linear transformation. Now let us discuss few examples of linear transformation. The first example is, we have considered T from vector space R2 to a vector space R2 which is defined by T of x1 x2 as x1 plus x2 to x1 minus x2. So let us see, we defined T from R2 to R2 as T of x1 x2 is equal to x1 plus x2 and it is 2x1 minus x2. Now suppose we want to show that this is a linear map or linear transformation from R2 to R2. So how can we proceed for this? So let us consider V1 V2 as two element in R2, two element of this vector space R2. So this implies V1 is something say x1 x2 and x2 is something y1 y2. Okay. And now we have to show that if it is a linear map, so we have to show that T of alpha V1 plus V2 is equals to alpha times T V1 plus T V2. This we have to prove if it is a linear map. So, how can we proceed for this? Let us find T alpha V1 plus V2 first. It is alpha times x1 x2 plus y1 y2. So, it is alpha x1 plus y1 and it is alpha x2 plus y2. Okay. So, T of alpha V1 plus V2 will be equals to T of this element, that means it is defined by this definition. So, it is simply T alpha x1 plus y1 plus alpha x2 plus y2, which is sum of these two elements in the first component, and 2 times the first component minus second component is the second element. So, it is 2 times x1, which is alpha x1 plus y1, minus x2 is alpha x2 plus y2. Now, this can be written as alpha times x1 plus x2, okay, plus y1 plus y2, comma, it is alpha times 2 x1 minus x2 plus 2 y1 minus y2. Okay. Now, this can be written as alpha times x1 plus x2, comma, alpha 2 x1 minus x2, comma, y1 plus y2 plus comma, it is 2 y1 minus y2. Okay, addition of these two. If you add this with this, you get the first component. If you add this with this, we get the second component. Now, this is nothing but, you can easily verify it is alpha times T of x1 x2. T of x1 x2 will be nothing but x1 plus x2 as the first component and 2 x1 minus x2 in the second component, and alpha times this will give the first component plus, and this is T of y1 y2. So, that is nothing but alpha times T v1 plus T of v2. So, we have shown that this property holds for every v1 v2 and alpha belongs to field. That means this map is a linear transformation. Okay. Now, similarly, we can easily show that T from R2 to R2, which is given by this expression, which is also called projection on the x axis, is also a linear map. It follows the same lines as we did earlier in the first example. So, now the third one is, we consider T from the set of all polynomials of degree less than equal to n over the field R to all polynomials of degree less than equals to n minus 1 over R, defined by T of f x is equal to f dash x. Now, this T is also called differential operator, okay, where f dash denotes the derivative of f x. Now, this is also a linear map. How it is a linear map? You can simply see here, we have defined T of f x as f dash x, where f dash x is nothing but derivative of f x. Now, you take any f and g in P and x, P and R, okay, and alpha belongs to field. Field here is R. You take alpha f plus g, T of this. So, T of this will be nothing but alpha f plus g whole derivative by this definition, and this is nothing but alpha of f dash plus g dash, and this is alpha times T of f plus T of g. So, we have shown that the property of linear transformation hold for every f and g in vector space Pn over the field R. That means this will be a linear transformation. Now, similarly, if we define a integral of a to b of a function f x, where f x is a continuous function from a to b, then this is also a linear map. Okay. So, this is very easy to show again, because if you take T of f x as all a to b f x dx, I mean T of f, I think T of f, yeah, it is T of f. If you take T of f defined as this, now you take any f and g in set of continuous function in the interval closed interval a to b and any alpha in field, and you take alpha f plus g, the T of this, that will be equals to integral a to b alpha f plus g x into dx, which is equal to integral a to b alpha f x plus gx whole dx, and which is equal to alpha times integral a to b f x dx plus integral a to b gx dx, and this is equal to alpha times t of f plus t of g. So, we have shown that this property holds for every f and g in the set of continuous function in the closed interval a to b and alpha belongs to field. This means this map is a linear map. Now, similarly, if we see the last example, you see we have considered A be a matrix, be a fixed matrix of order m cross n, and we define T as R n cross 1, means it is a column vector basically to a column vector of m dimensional space such that T x equals to A x. Now, again this A is fixed. If you take any x and y in R n cross 1 and take C x plus y, so it is easy to show that it is nothing but alpha times T x plus T y. So, it will be a linear map. Now, let us see some basic properties of linear transformation. The first property is, if we consider a linear map from V to W, V and W are the vector spaces over the field F, then the first property is T of 0 of V, 0 of V means additive identity of V, always map to additive identity of W. Okay. Now, it is very easy to show. We are considering here T from vector space V to W. What I want to show, if we have an additive identity here, which we denote as G or 0 of V, 0 V means additive identity of vector space V, always map to additive identity of vector space W by this linear transformation T. So, it is very easy to show. You see that for a linear map alpha V plus say P is equals to alpha times T V plus T P, and this is true for all V and P belongs to V and for all alpha belongs to field, since it is a linear transformation. Now, you first in this, in order to, we have to show that T of 0 V is equals to 0 W. Okay, this we have to show. So, you first put P equal to 0, since it is true for every alpha belongs to field and P and V belongs to V. So, it will be true for P equal to 0 also. 0 means 0 of course V. Okay. So, this means it is 0 of alpha V is equals to alpha times T V plus T of 0 V, because additive identity plus an element of vector space is itself, that is why we are having here alpha V. Now, in order to show that, now you take say alpha equal to, say you take V equal to 0, okay, you take alpha equal to 1, okay, and V equal to 0. Since it is true for every alpha and every V, so it will be true for alpha equal to 1 and V equal to 0 also. So, now we will obtain 1 dot V is always V. So, it is V, I mean V is 0 here, 0 of V, which is equals to 1 dot T of V will be T of V and V is 0. So, it is T of 0 V plus T of 0 V. So, let T of 0 V is basically, let us suppose it is W. So, we are obtaining W equal to W plus W. Now, W is the element of capital W, which is a vector space. Now, if it is a vector space, so its additive inverse will exist. So, you can always add with additive inverse of W both the sides. Element with its inverse give identity element. So, it is 0 of W is equal to W plus 0 of W. So, this implies W equal to 0 of W, and this implies W is nothing but you see T of 0 of V. So, this T of 0 of V is equals to T of 0 of W. So, this is the first most property that if it is a linear map, so T of 0 will always map to 0 of W, additive identity of W. The second property is T of minus V. Minus V is additive inverse of V. Okay. Always map to or always equal to negative of TV, that means additive identity of T of V. So, again it is easy to show. You see, we have to show that T of minus V is equals to minus of TV for every V in V. Okay. Now, we know that if it is a linear transformation, then T of alpha V plus P will be equals to T alpha V plus T P for all V P belongs to vector space V and for all alpha belongs to field. This we already know. Okay. Now, you put P equal to 0 first. Since it is true for every P, so it will be true for P equal to 0 also. 0 means 0 of V. Okay. So, it will be T of alpha V, the left hand side will be equals to alpha times T of V plus T of 0 V. Now, T of 0 of V is equal to 0 of W. So, it is alpha times T V plus 0 of W, which is equals to alpha times T V. Now, you substitute, put alpha equal to minus 1. If you put alpha equal to minus 1, we have already shown in the vector spaces that minus 1 dot V is nothing but minus V. So, it is T of minus V and it is minus 1 dot element of a vector space W will be minus times that element, that is minus of T V. So, we have shown this property also. The last property is T of alpha 1 x 1 plus alpha 2 x 2 and so on up to alpha n x n is equals to alpha times sum of alpha i's T of x i's, where x i's are the element in vector space and alpha i's are the element in field. Again it is easy to show, the result is very trivial. You see T times alpha 1 x 1 plus alpha 2 x 2 and so on alpha n x n. If you take this, now you take this element as suppose capital X. So, we know the property of vector space. So, by the property of vector space, this will be equals to alpha 1 times T x 1 plus T capital X. Now, it is alpha 1 x 1 plus alpha 1 T x 1 plus T of alpha 2 x 2 and so on alpha n x n. Again you take this as a capital Y. Again you apply the property of vector linear transformation. So, this will be alpha 2 T of x 2 plus T of y. So, similarly if you extend this up to n times, so we will get the same result which we are having here. Okay. Now, the next theorem is, let V be a finite dimensional vector space over the field F and let V1 V2 up to Vn be an ordered basis for V. Okay. Let W be a vector space over the same field F and let W1 W2 up to Wn be any vectors in capital W. Then there is a unique linear transformation T from V to W such that T of Vi equal to Wi for I equal to 1 to n. Okay. That what I want to say basically in this theorem, that you are having a linear transformation T from V to W. Okay. Here you are having some vectors, say V1, V2, Vn, which is an ordered basis of capital V. Okay. So, there will exist a unique linear transformation T, this T such that T of Vi will map to Wi, W1, W2 up to Wn. Okay, this is the main result, that there will exist a unique linear transformation T from V to W such that this happens. Now, proof is very easy. You see here, you take any, let V belongs to V. Okay. If any V belongs to this space, and this we already know that V1, V2 up to Vn is a basis, is a ordered basis for V. Okay. If it is a basis, this means any element V in this vector space can be written as linear combination of element of the basis, because it is a basis, that means this, the span of this will generate the entire vector space V. So, if you take any element V in this vector space that can be written as linear combination of elements of Vi's. Okay. So, this implies there will exist unique alpha 1, alpha 2 up to alpha n in field such that T of V will be V will be equals to alpha 1 V 1 plus alpha 2 V 2 and so on up to alpha n V n. Okay. Now, for this V we can define T of V as alpha 1, T of V 1 as W 1, T of V 2 as W 2 and so on. Now, this T is well defined and it is clear that T of Vi is Wi. Now, we have to show that this map is linear and number 2, this is unique. So, for linear, how we can show linear? You can take say V and P are two elements in W, in V. You take any alpha belongs to field and we have to show that alpha T of alpha V plus P is equals to alpha TV plus TW, TV. So, how can we show this? So, we have to prove this thing, T of alpha V plus P is equals to alpha times TV plus TP. So, this to prove. Okay. Now let P, since P is also some element in vector space V. So, this P can be written as some linear combination of element of Vi's. So, this will be beta 1 V 1 plus beta 2 V 2 and so on up to beta n V n, and this implies T of P will be beta 1, T of V 1 is W 1. So, it is W 1 plus and so on up to beta n W n. Now, you take alpha V plus P, okay, because you have to show this result for T as a linear map. Now, alpha P plus V will be what? It is alpha 1 plus, okay, alpha 1 plus beta 1 times V 1, this is P, this is V, plus alpha 2 plus beta 2 times V 2 and so on, alpha n plus beta n times V n. And what is T of alpha V plus P? This will be T of this, okay, this will be T of alpha 1 plus beta 1, okay, V 1 plus alpha 2 plus B 2 times V 2, alpha n plus beta n times V n. Now, this is equals to, it is alpha, it is, you see, it is alpha 1 plus beta 1 times T of V 1 which is W 1 plus alpha 2 plus beta 2 times T of V 2 which is W 2 and so on, alpha n plus beta n times T of V 1 which is W n. So, it is alpha 1 alpha times alpha 1 W 1 and so on up to alpha n W n and plus beta 1 W 1 and so on up to beta n W n, which is equals to alpha times T of V plus T of P from here and from here. So, we have shown that T of alpha P plus alpha V plus P is equal to this means this is a linear map. The next thing to show that this linear map is unique. So, in order to show that this linear map is unique, you consider a linear map U such that T of Vi is Wi for all I. Then if you write U of V from here, you see, if you take any V in again in V, then that V can be uniquely expressed as alpha 1 V 1 plus alpha 2 V 2 and so on up to alpha n V n. So, what will be U of V then? U of V will be by this expression, that will be U of alpha 1 V 1 and so on up to alpha n V n, okay, and this will be alpha 1 U of V 1 and so on up to alpha n U of V n, and this will be alpha 1 W1 and so on up to alpha n Wn. Okay. That means it is equal to T of V again from here. So, that means since the expressions are same, that means transformation is unique. So, we have shown that this is a linear map and the transformation is unique, hence we have proved the theorem. Okay. Now, the next is determine whether there exists a linear transformation in the following cases, and if exist, find the general formula. So, let us start with the first problem. Okay. If we are having say T from R2 to R2 which is defined as this expression, then can we find a linear transformation such that these property hold? How can we see? So, let us see. Let us start with the first problem. So, here it is T of R2 to R2 and here T of 1 2 is 3 0 and T of 2 1 is 1 2. Okay. First of all we have seen that these two elements are in R2. Okay. First of all, let us see, first of all observe that is are they linearly independent? So, answer is yes. We can't write 1 2 as a linear combination of 2 1. Okay. So, yes, they are linearly independent. Now, what will be the dimension of R2? Dimension of R2 will be 2, and if there exists any two linearly independent vector in R2, so that will be the basis of R2. I mean that will be the span of those two elements will generate the entire vector space. Okay. Now, these elements 1 2 and 2 1 in R2. So, the span of these two elements will be definitely R2 because they are linearly independent. That is what is the dimension of Rn? Dimension of Rn is n. Okay. And if you are having any n dimension, any set containing n linearly independent vectors, okay, so that will be the dimension, that will be the basis of Rn. There are infinite bases of Rn, there are infinite bases of R2. One of the bases is this: you take any two linearly independent vectors in R2, the span of this will definitely generate R2. This is one of the bases. Okay. Now, is there exists any linear transformation such that this equal to this and this is equal to this? So, and if yes, how can you find that? So, you see, you take any xy in R2, any xy here. Now, since this span of this generates entire R2, so that means there will exist some scalars alpha and beta such that this xy can be written as linear combination of these two vectors. Okay. So, this implies x is equals to alpha plus 2 beta and y is equals to 2 alpha plus beta. So, it is alpha plus 2 beta is equal to x and 2 alpha plus beta is equals to y. Now, you multiply this by 2 and subtract these two equations, what you will obtain? This is minus 3 alpha, okay, multiply by 2 and subtract with this first equation, and this is equals to x minus 2y, and that implies alpha is equals to 2y minus x by 3. Now, what will be beta? Beta will be nothing but y minus 2 alpha. So, beta will be y minus alpha is 2 by 3 times 2y minus x. So, it is 3y minus 4y, that is minus y plus 2x upon 3. Now, this xy is alpha times the first element, the first vector, and beta times the second vector. What is alpha? Alpha is 2y minus x upon 3 times 1 2 and plus 2x minus y upon 3 times 2 comma 1. Now, what is t of x comma y? Since t is linear, So, it is 2y minus x upon 3 times t of this, because it is some scalar, plus 2x minus y upon 3 times t of 2 1. So, this is equals to 2y minus x upon 3 times, what is t of 1 2? It is given here 3 0, and plus 2x minus y upon 3 times t of 2 1 is given as 1 2. Now, you can simplify this and we can easily find out what is t of x y. Okay. So, in this way we can find out a linear transformation t from R2 to R2. Okay. Now, if you see the second example, okay, here 3 elements are given to you, that is t of 0 1 is 3 4, t of 3 1 is 2 2, and t of 3 2 is 5 7. Of course, 0 1, 3 1 and 3 2 are not linearly independent, because the dimension of R2 is only 2 and here we are having 3 vectors. So, you take any two linearly independent, I mean any two Li vectors, say 0 1 and 3 1, find out a linear transformation as we did in the example first here, and if that linear transformation satisfy the third expression also, then there exists such linear transformation, otherwise we say that linear transformation does not exist. So, if we have a conditions here in the first example, we are having 2 conditions only and the vectors are linearly independent. Okay. Here we are having 3 vectors. Okay. So, basically if you have to see that such linear transformation exists, then you can write 3 2 or 3 1, any one vector as a linear combination of remaining 2 and try to see that whether the expressions are also same or not, images are also same or not. If they are not, that means that linear transformation does not exist. Okay. Now, for the third example, you see it is defined from P2 to P2. P2 is a polynomial of degree less than or equal to 2. So, what is the dimension of P2? Dimension of P2 will be 3. So, for a unique in order to find a unique LT, unique linear transformation from P2 to P2, we must have at least 3 independent conditions, but here the conditions are only 2. So, this means there exist infinitely many linear transformation, from P2 to P2 here. And if you are interested to find out one such linear transformation, then you take a vector independent of this and this, take any image of this and that, then you can find out. Say for example, here what is given to you, t is from P2 to P2. Okay. Now, t of 1 plus x is x plus 2, okay, and t of x square is 4x. Only 2 conditions are given to you. So, there will be infinitely many linear transformation from P2 to P2 satisfying these 2 equations. Suppose we are interested to find out one such linear transformation. So, how can we proceed? You take t of say x as, okay, say x square. This will make these vectors as linearly independent, these 3 vectors as linearly independent. Okay. You can easily verify that these 3 vectors are linearly independent. Now, you take any polynomial of P2, say a plus bx plus cx square, that can be written as alpha times 1 plus x plus beta times x square plus gamma times x, because these 3 vectors are linearly independent. And how many vectors these are? 3, and the dimension of P2 is 3. So, this will form a basis of P2. So, any vector in P2 can be written as linear combination of element of the basis. Now, this implies, if you take here, the constant here is alpha. So, a is equal to alpha, the coefficient of x is alpha plus gamma, and that is equal to b. The coefficient of x square is beta, which is c. Now, this implies gamma is equals to b minus a, because alpha is a. So, we can say that a plus bx plus cx square will be alpha times, alpha is a 1 plus x plus beta is c x square and gamma is b minus a times x. Now, you take t of a plus bx plus cx square, that will be equals to a times t of 1 plus x, c times t of x square plus b minus a times t of x, and that will be equal to a time t of 1 plus x is x plus 2 plus c t of x square is 4x plus b minus a t of x is x square. So, that will be equal to basically b minus a times x square plus 4c plus a times x plus 2a. So, this is the required linear transformation, one such linear transformation. So, there are infinite ways to consider the third expression. So, there are infinite linear transformation of such type, but one such linear transformation is this. So, in this way we have seen that what linear transformation is and what are the basic properties of linear transformation. Okay. Now, there may be some examples, say you consider t from R2 to R2 as t of say x y as 1 plus x comma y. Now, it is not a linear transformation, we can easily verify this. You see, if you take t of 1 0, it is simply 2 comma 0. If you take t of 0 1, it is again 1 and 1. If you take t of sum of these two, that is 1 and 1, sum of these two is 1 and 1, that must be equal to sum of these two by the property of linear transformation, but by the definition it is coming 2 comma 1, which is not equal to sum of these two. So, that means it is not a linear transformation. Now, similarly, if you define say t from R2 to R2 as t of x y is equal to say x square comma y, it is also not a linear transformation. It is very easy to show, you simply give a counter example for this. Okay. So, in this lecture we have seen that what linear transformations are and what are the basic properties of linear transformation. In the next lecture we will see some more properties of linear transformation. Thank you.